random early detection differs from DECbit in two major ways. Number one, rather than sending a congestion notification, RED implicitly notifies the source of congestion by dropping one of its packets. So RED implicitly notifies the source of congestion by dropping one of its packets. So there are no specific congestion bits are used to indicate a congestion. And the second thing is RED decides when to drop a packet and what packet to drop based on a drop probability, right? So if it has to do packet dropping, and the question is how RED decides, for one, when to drop a packet, and number two, which packet to drop. So these are two important decisions that we have to make in RED, and this happens with some drop probability. So when to drop a packet and which packet to drop is happening with some drop probability. Whenever the queue length exceeds some drop level. So this means the routers using RED maintains a certain drop level, and whenever the queue length exceeds the drop level, we drop a packet based on a drop probability, right? And that's why the idea is called. That's why this idea of dropping packets early with a probability is called. The idea is called early random drop. Early random drop. Okay. So, so in order to understand random early detection, it's important to understand the computation of average queuing length, because we will drop a packet with certain probability if it's exceeding the queue length. So let's talk about how we can compute the average queuing length. So computation of average queue length. Okay, so so the queue length or RED calculates or computes the average queue length using this formula. RED calculates the average, computes average length using this formula S. So average length is equal to 1 minus weight into previous value of average length plus weight into sample length. Okay, so we use this formula to calculate what? To calculate the average length, and you can clearly compare this formula with the calculation of sampled RTT, right? So there we also calculated the average value of running value of sample RTT in a similar way, right? So in this example, the weight is between 0 and 1. The value of the weight is between 0 and 1, and the second parameter that we are taking into consideration is the sample length, and sample length is the length of the queue when a sample measurement is made. Is the length of the queue when a sample measurement is made. Let's try to understand this with the help of an example. That why do we need to have the average length into consideration? So let's try to understand the need of having this average queue length with the help of this scenario. So what this figure represents is that the queue length is represented as a function of time, and usually we have a burst of traffic in the network in clusters, so there's a possibility that the queue length increases for some specific amount of time, and then we have done with transmitting all the packets in the queue, and again we have a burst, and then we're done with the transmission of the queue, and the queue length is again reduced. Then we have again increase in the the traffic, or we have traffic burst here. So what is happening here is that we have a very inconsistent changes in the queue length, obviously because we have traffic burst. So instead of using this value for the calculation of the probability to when to drop a packet or to calculate an average queuing length, so queue length, why not to take an average queuing length into consideration, which is more smooth for calculating the average, for calculating the probability of drop. So in order to calculate the average queue length, the RD has two thresholds. So how we will calculate this average queuing length? For that we have in RD, random early detection has two queue length thresholds. Okay, one is called minimum threshold, and the second is called let's try to understand this with the help of this queue diagram. So let's assume So that is a queue that is being maintained by RED. Okay, and this value here, say, identifies the minimum threshold, and say this value here, somewhere here, identifies max threshold, right? So the average queuing length will be somewhere here. Right? So in order to calculate average queuing length, we have two thresholds. We have a minimum threshold and we have a maximum threshold. So we try to understand how this average length is computed using minimum threshold and maximum threshold values. So how RED calculates the average length with this minimum and maximum threshold. So if average length is less than equal to minimum threshold, then obviously queue the packet. So it's somewhere here less than the minimum threshold, so we will keep queuing the packets. If minimum threshold, or if it is between the minimum threshold and maximum threshold, then we have, if it's somewhere here, which is in the diagram at the moment, the figure at the moment. So if it's between the minimum threshold and maximum threshold, then this means we have to calculate probability P, probability P means drop the arriving packet with probability P, right? And the third condition is that if max threshold is less than equal to average length, drop the arriving packet. Right. So if again we look at this diagram, so if this means if the average length is less than this minimum threshold, we'll keep queuing the packets. And if it is between the minimum and the maximum threshold, we'll always calculate a probability with which we will be dropping the packets. And if this average length is somewhere greater than this maximum threshold, obviously every packet that is arriving at the router in this queue will be dropped, right? So the probability of dropping as a function of average length, but situation is actually a little more complicated. So let's try to understand this drop probability with the help of this figure. So let's assume that this probability of drop is represented as a function of average length, right? And we have obviously two thresholds. We have min thresh, and then we have the maximum threshold. Right, and then on the probability we have max p, maximum probability p, and then we have probability 1. Right, so what happens here is, just to understand it, that we increase slowly the probability of drop, and when it reaches this maximum probability, we start dropping all the packet, and if still the average length is greater than the maximum length, maximum threshold, all the packets will be dropped. So, so this means, though we are representing the probability of drop as a function of average length, but the situation is actually a little more complicated, right? Because p is a function of both the average length and how it has been since the last packet was dropped. So it's more complicated than this simple representation of drop probability as a function of average length. Why? Because the probability p is a function of both average length and, importantly, how long it has been since the last packet was dropped. Because this will help us in order to make sure that the packets are not dropped in clusters. Because if this is happening, that the packets are dropped in clusters, this means the sender will again go back to slow start phase. So this we don't want using this random early detection algorithm. So what we do basically is we calculate the probability in this way. TemP is equal to max p probability into average length minus minimum threshold value divided by maximum difference of these two thresholds, maximum threshold minus minimum threshold. Right, and then this TemP is used to calculate the drop probability p. So p is equal to TemP divided by 1 minus count into TemP. Right, so here this TemP is the variable that is plotted on the y-axis in our diagram. So TemP is the variable that is plotted on the y-axis. Okay, and the count in this count, we are familiar with all the other parameters, and the count here keeps track of how many newly arriving packets have been queued. Not dropped. So obviously this will help me to identify how it has been doing since the last drop. So if P increases slowly as the count, P obviously increases slowly as the count increases, thereby making a drop increasingly likely as the time since the last packet drop increases. So it's very important to note that P, the probability increases slowly. Slowly as count increases. Why? Because the count is representing that how many newly packets have been queued without a drop, right? Thereby making a drop increasingly likely as the time since the last packet last packet drop increases. Right. So this makes us to understand this important point that this makes closely spaced drops less likely than widely spaced drop, right? So extra step in calculating this P is to avoid drops in clusters. So this extra step in calculating this, P is to avoid drops in clusters, right? So why we want to avoid these drops in cluster? Because if this happens, the sender will result in, this can result in, if this happens, this can result in slow start at the ends, right? And we do understand what we mean by this slow start, because obviously this will then slow down the sending rate, So let's try to understand this with the help of an example to see how RED will behave considering this diagram. So let's assume that we have a max P value of 0.02. Let's try to understand this with the help of an example. How does it work, right? So max P is equal to 0.02 and count is 0. So if average length, let's assume if average length were half between the two thresholds, which is the case over here in this diagram, right? So let's assume if the average length were half between the two threshold values, then TemP, and the initial value of P would be, so then obviously TemP and initial value of P would be half of max P. What is max P? 0.02 or the half of max P is 0.01. So, so what's the scenario? We have a scenario where the max P is 0.02 and the count is 0 and the average length is between the two thresholds. Then the value of this TemP and the initial value of P is half of the max P or 0.01. So if an arriving packet, if a new packet arrives, obviously there are 99 in 100 chances that it will get into the queue at this point, right? But P is what the P is. What is happening here is that P is increasing slowly, right? And let's assume that it has been a case that there. Let's assume that by the time 50 packets have arrived, so let's assume by the time 50 packets have arrived, without a drop. So P would have reached to, P would have reached to 0.2. So this means P would have doubled. This means what? This means this value is 0.02, which is the max P, right? Now, in the very unlikely event that 99 packets arrive without a loss, P reaches 1, right? So if we assume that there has been no packet drop here, let's just assume it, and this means now P is at 1. This means what? Every next packet will be dropped from the queue, right? So here we were assuming that max P is 0.02, and the queue length is between these average length is between these two minimum threshold values, and we are slowly increasing its size. And by the time when we have 50 packets without a drop, we assume that the max probability or the probability is equal to max P, which is 0.02. And if we still believe that there has been no drop, which is very unlikely, this means the probability will become 1 in this case, and every other packet will get dropped from the queue, right? So, so this means if we want to conclude that the RED ensures a roughly even distribution of drops over time, and it's very important. So, RED, random early detection, ensures a roughly even distribution of drop over time, right? And why this is important? Why this is important? Yes, it's important because this will make sure that drops are not happening in clusters, and if If drop on contrary, if drop happens in clusters, this means the center will start into a slow start. And this concludes our today's lecture. So today we'll talk about the different resource allocation mechanisms. First, we establish a case that we need to have resource allocation mechanism in addition to typical congestion end-to-end congestion control mechanism. And then we started discussing the evaluation criteria of different resource allocation mechanisms, and then we tried to understand the different service models and the taxonomy of congestion control algorithms, and then we discussed the most important part of congestion control, the most important part of resource allocation mechanism, the queuing disciplines. Then we discussed the two very common queuing algorithms, first in, first out, and fair queuing. And then we also talked about that we can enhance, so we can force the routers or the network elements to assist in congestion avoidance. And for that, we need to understand active queuing, active queue management, AQM, and in active queue management, we talked about DECbit and random early detection.